Hello, everyone. Good morning, good afternoon, and good evening to everyone who's tuning in. On behalf of PioPetro, Arab Oil and Gas Academy, and SPE Egypt section, I would like to welcome you to today's session. My name is Shahid Bahjat. I'm a third year petroleum engineering student from Kurdistan, Iraq, and I'll be your moderator for today. Before we start, I'd like to remind you to please drop your questions in the Q&A section below. Please keep the chat box professional and ethical, and please submit your quizzes before the deadline. Now, without further ado, please give a warm welcome to Dr. Medhat Kamal, who will be giving his webinar on natural gas well testing. Medhat Kamal is a Chevron Emeritus Fellow and SPE Honorary Member and a distinguished lecturer with over 40 years of industry experience in well testing and production and reservoir engineering. He is the editor and lead author of SPE Monograph 23, Transient Well Testing, and has published more than 35 papers in referred journals. He holds BSc from Cairo University and MS and PhD from Stanford University in Petroleum Engineering. Kamal was an SPE board member and served as the executive editor of SPE REE. He received several regional and international awards, including the Cedric Ferguson Medal and SPE Formation Evaluation Award. Dr. Medhat Kamal, thank you so much for coming, and the mic is yours.
Thank you, Shah. Good morning, good afternoon, and good evening to everyone. And I thank the Arab Oil and Gas Academy for inviting me to share this lecture with you. I hope you all can see my slide. And I'm going to start talking about gas well testing. I need first to say some few words about testing in general before we get into the specifics of gas well testing. So when we talk about reservoir engineering in general, we are actually talking at what we call an inverse problem. One of the challenges that we have in petroleum engineering, and actually one of the distinctions we have, is that we work with systems that we did not design. They are given to us, and moreover, we cannot actually physically access them. So what we need to do is that we need to identify what this system. The way we do that is that if we have a reservoir model, like the one you see on the left side of your screen, we actually perturb that reservoir and watch how the reservoir reacts to that disturbance. And then we have a model, and this model is actually based on the physics. And we actually, in that model, we send the same input as we perturb the reservoir, watch the response of the model. And what we try to do is that we try to make sure that the model output and the reservoir response match. And from there, we can deduce what are the reservoir properties. Specifically in well testing, we do the perturbation by, first of all, lowering a pressure gauge into the well bore. And then most of the time, we change the flow rate. And when we change the flow rate, we watch how the pressure in the well changes with time. And as you see in that picture, we try to match the data collected from the well, the dotted points you see there, with the model calculated solid curve you see. And when they match, we know that the properties we entered in the model we can consider them to be the same properties in the reservoir. The process we use when we do well testing, first of all, we start, you can see there by the start box on the top left, and then we collect the data. And as engineers, the first thing we do when we collect the data is to do the quality control and quality assurance for the data, make sure that we have good data. And if we don't have good data or enough data, we actually do it again. Once we have good data, we look at the data and we do, for the well test, that we identify different flow regime. One flow regime that has to do with the well bore properties. One flow regime has to do with if there are fractures around the well. One flow regime that has to do with the reservoir properties itself. And then once we identify the flow regime, we actually will select a well and reservoir model based on that. In order to do this, we will usually most of the time need some help from additional data like from geology, well logs, cores, well completion, production data, etc. Because we are faced with a problem where we may have more than one solution to fit the data. Once we selected the reservoir model, and we actually go ahead and we say, we're going to calculate what the reservoir properties from this model. And then these properties we calculate from each flow regime, we will calculate properties that relate to that flow regime. But then we need to actually go do some regression analysis in order to match the entire test response. And if we have an acceptable match between the collected data and the results from the model, then we're done and we can complete our report. If we don't, then we actually have to go back and calculate the other reservoir properties or modify them and go through the process again until we match the data. This is how we work with general pressure transient testing. And the main plots we use in doing the result is a plot, is the way you're looking at it here. This is called the Bourdais derivative. This is the curves on the top are the actual pressure versus time data, and the curves on the bottom, these are the pressure derivative of the first derivative of this pressure data, and this is how the model look like. When we have a flat line there, this is a part of the data that describes the reservoir. We have the data at the beginning here, we have a slope of 1. This is the part that describes the wellbore, and so on and so forth. There are other flow regimes that we look at. Now, when we talk about gas wells specifically, we figure out that in the development of the transient data, the transient testing models at the beginning, we actually use slightly compressible fluid like oil and water. Now, when we talk about gas, then as you all know, the gas properties are strong functions of pressure and temperature, and therefore they are not what we call a slightly compressible fluid. So when we use the equation of a state for the gas, which you all are familiar with it, and it's described in here, then we need to use this information now in order to analyze the data from well test. So what do people did long time ago? What they did is that they said, well, okay, if the reservoir pressure is greater than something like about 6,000 psi, then mean the pressure is high enough and the gas will actually perform like liquid. And for that part, they actually simply went ahead and analyzed the data using pressure versus time, just like they did with oil and water well. And then they said, well, if the pressure is less than 2,000 or 3,000, something in this range, then the properties of the gas would say that the viscosity and the compressibility is constant, and we actually can use the square of the pressure rather than the pressure in analyzing the data. And now this part in the middle here became the no man land, where really none of these two methods worked very well. However, there is a lot of literature, a lot of work done, and actually uses both the pressure and the pressure square. And then in 1966, Rafi Al-Husseini and Hank Ramey, they were doing research at Texas A&M University, and they provided us with a new solution. They said that rather than using either the pressure or the pressure square, you can actually use this function that is called the pseudo pressure function. And you can see the pseudo pressure function is the pressure over the viscosity and the compressibility. It's an integral of this parameter over a range from a given standard pressure to the actual pressure that you have. And the point that they made is that you actually use if you use the pseudo pressure function, then this function is actually valid no matter which pressure you're in. The point that we need to remember here is the pseudo pressure is actually an integral, and you all know integral is like an area. So it's like it's the area under this curve. When I say what is the pseudo pressure at pressure P, then actually we're talking about this green area here under that curve. So the value of the numbers of the pseudo pressure are usually something like 6 times 10 to the 12 to the 6, or 7 times 10 to the 6, large number. Some people don't like to look at the number that way. They like to look at numbers closer to pressure number. So they figure that maybe we can use something called the standardized pseudo pressure, in which they simply divide the pseudo pressure by the reservoir pressure, and this way they find numbers closer to pressure, but doesn't change anything as far as the analysis. So the pseudo pressure function is actually a function that I said will valid for no matter which pressure that you have, it will work for you. And we do the analysis with the pseudo pressure just similar to the analysis we do for slightly compressible fluid like oil and water. Now, one of the other important things about gas wells is that because the viscosity of the gas is very low, then the flow rate in the well inside the reservoir is very high. And when you have high flow rate in the reservoir, then that gets you to be looking at turbulent flow, not laminar flow. Of course, all the equations that we have were developed assuming that we have laminar flow. So if we do not take into consideration the effect of the turbulent flow that we have, then we have turbulent flow. This means that the pressure drop is much higher than if you have laminar flow. If you don't take into account the fact that you have the turbulent flow, you have this larger pressure drop, and that larger pressure drop will actually show up as damage. We all know that one of the parameters we calculate from pressure transient testing is the damage. But if we are not careful, that the number that we calculate is actually a number that's made of several parameters. The actual damage around the reservoir. We also have something about if we have the partial penetration, if the well is not completely penetrating the reservoir, if we have something about the perforations that are not completely functioning properly, something about if we have fractured, if we have segmented well performance, and so on. All these, there are other things that beyond the scope of this lecture, we'll talk about these points here. But in this lecture, what we really wanted to talk about is that we wanted to talk about how do we take care of the turbulent flow in our because of the flow rate of the high flow rate of the gas in calculating our the skin. So we actually know what the actual damage, if there is damage around the well, not think about it as higher damage because of turbulent flow. So the actually turbulent flow, the skin of the turbulent flow is actually a function of the flow rate. So actually you can think about it as a constant time the flow rate. So now you can see that the equation of the total skin is like an equation of a straight line where this is the slope and this is the intercept. So the equation would look something like this. So in order to find out what is the actual skin, what we have to do is that we have to actually run a test at different flow rates, and then we make a plot like this where you actually have the measured skin versus the flow rate, and you have different points like that from the different flow rate. And when you extrapolate this line to a flow rate of 0, then the intercept would be the actual skin. I would like to show a demonstration here for this part. So I'm going to go ahead and change the screen that I'm sharing. I'm gonna open that icon there on the left. This is called Sapphire. kappa have different parts, but the pressure transient, and that's called Sapphire, which you can see now. And with that, I just put the reference time, and I'm going to say next. In this example, all that I'm trying to do is that I'm going to try to demonstrate the concept. So we are not going to be worrying specifically about the specific parameters. One of the things that you can see on this screen you see here is that there are some parameters and they are marked or colored in red. This is actually something that we need to give credit to the engineers from Chevron who actually came out with the idea and suggested it to kappa that whenever there are values that are already in the thing, not the values that the engineer want to input, but the values that are there, they need to be marked in there so the engineer recognize that I need to change this number because they are just simply not what I have. So when I go to say next, then in that specific software, I'm going to say that I'm analyzing a gas well, and you look at this what flask that with properties. One more time, in this example, we're just going to simply use the parameters that already exist there, and we are going to do that, and we're going to start loading the data that we have. The first data that we need to load are the flow rate. Actually, in the software, you follow the icons from the top to the bottom that give you the steps you want to take. So the flow rate, I have the flow rate. I already have a file for that, and I am going to click on that file and open it. And in order to characterize these numbers, the program show them like that. I'm just simply mainly getting the program to work. I'm not my intention in this lecture is not to show to teach people about software. I'm just using the software to show a problem. So I'm gonna load the flow rate, and then we're gonna do the same thing for loading the pressure. I'm telling the program that I have a file where I have my pressure, and again I am going to tell the program make sure that I have the things like where the time and the pressure are, and we're going to say load, and this is a simple. All right, so you see in this example here, what we did is that we have flowed the well. We have flowed the well at different rates, and at the end of each one of these rates, we have a buildup, a short buildup, and then at the end we have a very long buildup. This is usually the way we run the test. Now, for do the analysis, we're going to start by first of all extracting which pressure we're going to be working with. And the program usually understand that you most likely want to use the last buildup, so it will allow you to extract it. And if I say OK, then the program part of the default is that say I know that if I draw a flat line, then that will give me the value of the permeability. A unit slope line will give me the value of the wellbore storage. So that's what the initial thing from the software, and I want to do an analysis on it. So I'm gonna one more time. I'm going down there. So I'm gonna go to the analytical model, and I'm going to say generate the model. And now you can see that what the model I have, it's not bad, but I can actually improve on this match. So I'm gonna go to the improve part, and when you go to the improve, you have the right to select which parameters you want to regress on. We are going to use this parameter, the permeability, the skin, and the wellbore storage. I'm going to say run. Then the program actually, you can see, have a very nice match. But this very nice match was because we analyzed the data from the last buildup. So if you look here on the history plot, you see that I have a very nice match at the end, but And when I have a different flow rate than this last flow rate, the match is not very good. Actually, you can see that the match in this flow rate here, the second flow rate, is a little bit better because the second flow rate is the closest one to the final flow rate. The main reason for that is that because of the different flow rates, there are different skin. The higher the flow rate, the higher the skin. But I'm only using in this analysis one skin that I calculated from the last flow rate. So what we need to do now is that we need to actually, in order to do the analysis right, we need to take into consideration the changes in the flow rate. So I'm going to tell the program that I also want to be able to use different buildups, not only the last one. We're going to use buildup number 1 and buildup number 2 and buildup number 3. And we're going to say okay to that. Then you can see that that all the buildups are being plotted here. I'm going to say okay to that. And then right here, you see that these are the calculation from the buildup. We're going to, if you look at the slope here from all these buildups are similar because the slope is an indication of the permeability, and the permeability is the same. But the level of the line is different, and that because of the different skin. So in order to do this analysis, we are going to, I'm going to right click, and I'm going to tell the program I want to use multiple lines, and I'm going to say that I want to use multiple lines I'm going to start with from buildup number 4 because that's the one I started with, and then I'm going to come here and I'm going to tell the program which data I'm going to use. All the buildups are much shorter than the last one, so this is actually the only place. Oops, this is actually the only place. Maybe I better go to the individual part. The only place where I actually have all the buildup, and now you can see that I have all the straight line there, and the program based on it from each one of the straight line, it calculated the skin, and now it gives me a plot of the skin versus the flow rate. So in order now to do the match with the on the history plot, so I'm going to go to this dashboard one more time. I really do not, it's not my intention to teach software. I'm just using the software to show the concept. So I'm going to go here and say that I want to look at the similar log result. And you can see that here it's saying the similar log result. This is the skin at the flow rate of 0. It's only 3.5. If you remember, when you run the program at the beginning, it gave a skin of about 8 something. That actually was the skin at the last flow rate, but part of it was because of the turbulence. This is the skin at 0, and this is the slope of the line. So if we take this data and we move it to the analytical solution, you can see that now I have a much better match on all the flow rate. I can actually also now, if I need to, maybe I should need to go. Now these are the results. You can see that I have the actual damage, and one of the things, one more time, is that because we use default numbers in this model, the software is warning you that you actually have used some default values. You did not input numbers yourself everywhere. We can one more time improve on that. So if I go to improve, and I want to say that want to improve, I actually want to improve on the history plot, not on the log plot. So I'm going to say that I'm improving the history plot, and I'm going to say run. And the improvement is a little because we start with a good numbers, with a good match. So now this is the final result that I have when I now know exactly what my skin is, 3.9, what the slope of the line is, and again, what the value of it. That is all what I needed to do for that example. So I'm going to now close this model demonstration. All right. So the next item we need to talk about for gas well test is that we need to talk about we need to talk about the deliverability testing. This is one of the things that are different for gas well than for oil well, because you produce gas from wells and you don't store it in tanks. You actually have to immediately transport it to wherever you're going. So, and so there was a question about deliverability testing. It's a nice story. I think it's very important for people to recognize what is the origin of the deliverability testing. In the United States, there are states that are rich in oil and gas. Some states are not. So people who are actually producing gas from oil-rich states were actually producing gas at very high rates. And there was a question about if everybody produces their gas at that highest possible rate, two things are going to happen. Number one, the price of gas is going to decline, and they are going to exhaust all the resources. So they figured out, no, we need to figure a way to actually control the production of the gas from all the states to keep the price reasonable and to continue to keep our resources. If you actually think about it, this is the original OPEC, but it was only for gas and between states. So they developed something which said, how much can you produce your gas well? And the point is that depends on the deliverability of your gas well. If your gas well can produce at a higher rate, we will allow you to produce a higher rate. And if your well cannot produce, then we're not going to allow you to produce. And now you have to figure a way to measure the deliverability or the ability of the well to deliver. Then after that, the thing developed and it became an important parameter. For example, when you are negotiating a gas contract from company to for a company who's going to use your gas in something like generation of electricity or producing fertilizers, they need to know that you are actually going to be able to provide this gas at the rate you described for a long time. So they deliver the things called the deliverability test. And originally, it started by looking at figuring out empirically the point that you look at the flow rate, then the flow rate of the well is actually can written as an equation like that. This is a constant, and this is average reservoir pressure squared, and this is the flowing pressure squared. This is to the power n. Right now, by the way, we don't use the pressure square anymore. We use the pseudo pressure function as I mentioned before. So if you take the log of this equation, it looks something like this. You can see that looks like a straight line on a log-log plot, where this is the slope, 1 over n, the slope of the straight line, and c, 1 over c, that is the intercept. So if I actually look at, make a plot of the flow rate versus either the difference in the pressure square or the pseudo pressure, then you can find that I can have a straight line. The slope is 1 over n. And the point is that if I flow my well, excuse me, if I flow my well and then get to the point where I have it completely open, in other words, there is no back pressure, I have it completely open. Oops. I have it completely open, then at that pressure, then this is the flow rate. Then this is the absolute open flow rate. And based on that absolute open flow rate, then that is what's going to be determining the deliverability of the well. So the point is that who's going to do that? I mean, you're not actually going to open your well and let it flow for a long time in order to do that, because what happened is that when you look at the behavior of that, the slope of the line is going to be the same. It doesn't matter how long you flow the well, but then the intercept C is actually decreases with time as long as you produce through the well, and asymptotically it gets to the point where this is a value of C that we wanted to use. So in order to do that, we said, okay, if I produce my well at this different flow rates, and then at one time, I mean, at some time, I measure the pressure, then I'm going to have on the straight line that look like this. Now, if I instead of flowing my well at this time, I'm going to flow it longer time, then I'm going to find a straight line, again, the same slope, because 1 over n is the same. However, as time goes by, I find that that straight line is going to keep on shifting to the left in order to get me to the point where I have calculated the value of C. So people figured out, okay, I really don't want to flow my well for a long time. So they figured out there are different ways of doing that. Now, the point is that if you flow your well at the beginning at small flow rate, then you have laminar flow, and the data would look something like this. N is 1. If you flow your well at a high rate, then you're actually going to go into turbulent flow, and then your data are going to follow this line. Usually, then your data are going to go from small flow rates to the high flow rate. And if you're going to calculate the absolute open flow at that very low pressure at the wellbore, then that's going to be your absolute open flow. However, as you can see from the plot, if you actually use the laminar flow line, you calculate a higher absolute open flow rate. So somehow they have an agreement at the beginning that this is the line from which you are going to calculate the absolute open flow rate, not the real number. That's the way they agreed, and that's the way it is. So how do you actually run the test? There are several ways. First of all, people said, we're going to flow the well rate after rate and measure. And then there are other two things I'm going to show in a minute. The first two cases that you say, I'm going to flow my well at different flow rates, and every time I'm going to wait until I reach steady, like constant pressure, or the pressure doesn't change much, and from there I'm going to get the data and make my plot and calculate my absolute open flow potential. And then people say, wait a minute, I don't want to flow my well for a very long time all the time. In order to calculate that, you need to reduce the test. You can see here, these are very long times. So the came idea was the isochronal test. Isochronal mean equal time. So I flow the well at a given rate, and while I'm flowing the well, I'm actually going to be measuring the pressure at these specific times, 1, 2, 3, 4. And then I'm going to shut the well in, and I'm going to wait for the pressure to go back to the original pressure. And then I'm going to flow it again at a higher rate. I'm going to flow it again at a higher rate and do the same thing, calculate the pressure at the same times, 1, 2, 3, 4. And then I'm going to shut the well and wait for the pressure to go back to the initial pressure. Now you can see, because I flowed the well at a higher rate, it's going to take me longer to get back to the original pressure. And I'm going to do that for all the other flow rate. And then, as you say, people are never satisfied. They say, no, wait a minute. Every time I have to use a higher flow rate, I have to shut the well in for a much, much longer time. And that's wastes a lot of time. So the final case was that the modified isochronal test, where you don't shut the well in until you reach the initial pressure. You actually shut the well in for a time that is equal to the flowing time, no matter what. And the difference here is that when you're actually calculating the value for your plot, instead of using the reservoir pressure at every one of this flow rate, instead of using the reservoir pressure to subtract from it the flowing pressure, you actually use the pressure at the beginning of each one of these steps. And by doing that, it was shown that you will be able to get exactly the same result as if you run an isochronal test. So the modified isochronal test is the way it's done. And if you remember now, in the example that I showed you was when I was showing the software, that is exactly what was being done. So I was asked also I need to talk a little bit about the unconventional resources. So the unconventional resources have, as I say, good news and bad news. The good news is that the unconventional resources, you have a very large volume of them, very large volume, because we are not really actually looking for reservoir quality. We're not looking for reservoirs where gas has migrated and kept in there. We are actually looking for source rock where actually the gas is there, but the permeability is low. So the good news is that we have a lot of it. The bad news is that the permeability is very, very low. Actually, the permeability is in the nanodarcy. So when I try to analyze data from unconventional reservoir, before I get to that, I just want to say something that when actually people started producing this unconventional or actually tight reservoir, that became very important thing, especially in the United States, where there is a lot of production of oil and production of gas. And as all of you probably know, in the last few years, the United States became the largest producer of hydrocarbons. This is oil plus gas. And also the United States became self-sufficient. Now, one of the good news that happened with producing a lot of gas and using a lot of gas rather than using oil or even coal, because that's the production. One of the advantages that happened is that as they increase the production of gas, actually the carbon dioxide emission decreased considerably, and that will be helping us later on. I need to give credit for these two slides to Dr. Naomi Bonis from Stanford University. She gave them to me. So now, let's go back to the point we're making. If I'm trying to analyze data from unconventional reservoir, as you all know, unconventional reservoir, we drill a well, and it's a horizontal well, and then we actually have several fractures along the horizontal section, and this is how we're able to produce at commercial value, commercial quantities. So if I actually look at data that I collected from testing unconventional reservoir, first of all, I'm going to find data that tell me that I have a fracture. Then I'm going to have some data that tell me that there is an area around the wellbore that I fractured it and I'm producing from. Then I'm going to have data that horizontal line, just like the horizontal lines we saw in the previous example, that tell me the reservoir properties, the permeability, and then finally a line that tell me what do I have as far as the volume. So when you look at that, you say, hey, what's the big deal? I can actually run a test, and I found all these parameters. The point is that, for example, in order to with tight formation, in order to reach this straight line, you actually need to run the test for something about 50,000 years. And I doubt that any of the engineers listening to me now are going to go to their management and say, if you let me shut the well in for 50,000 years, I'll come back and tell you something good about your reservoir. Of course, we're not going to do that. So we have to find other ways in order to characterize the reservoir. So the main things that we do, there are three major items we use. One of them is that actually we use the data during the fracturing to give us some analysis, diagnostic analysis. We actually used in decline curve analysis and rate transient analysis, and I'm going to talk about a little bit about these. You probably, all of you, recognize what decline curve analysis is. Maybe talk about a little bit in a minute, based on how much time we still have. So the diagnostic fracture analysis, we actually, while we are fracturing the well, we measure the pressure versus time. And this is the breakdown. This is where we end up pumping. This is the initial shut-in. This is actually when we broke the formation. And from the slopes of these different parts of the curve, we can say something about the permeability of the reservoir. It is not as close to the actual number as if we actually had run the test, but we're not going to be able to run the test. So the other thing is that you say, I don't have to actually run a test, but I'm going to start producing my well, because that's what I need to do. I need to produce my well, and then I'm going to look at the production data, and from production data, I am going to characterize my well. This is when we say that we're going to use decline curve analysis. Decline curve analysis, as most of us know, is something was developed back in the 1920s, where we actually say, very simply say, if I make a plot of the pressure versus rate, of the pressure versus time, while I am producing my well. I can make, if I produce a well at a constant pressure, I can see how my rate is going to declining with time. And if I say, if I take a part of that line, the last part, and I extrapolate it a little bit by little bit, I'm in good shape. This is what the decline curve analysis is. Now, ARPS in the 1923 actually started to say, I can write an equation, a mathematical equation to describe this curve. This mathematical equation doesn't have any physics in it. It's just simply say, I am going to plot a mathematical function to match the data. By the way, if this is exactly what machine learning is. When you hear a lot of data about machine learning and data analytics, this is exactly what happened there, except the equation we use now are a little bit more sophisticated. So ARP's equations say that I am producing my well at constant bottom hole pressure, and I'm seeing how the rate change. But however, in order this would happen, I must be in the boundary dominated area. That of course could take much longer time to reach in unconventional reservoir. So people started using different modifications to the ARPS model in order to find out how do we actually be able to have a better match for the data. And then when you actually look at the data, at the different models, you find that we have a little problem. This example you're looking at now, we have data, and you can see at the beginning, I have a very good match between the models, the different models that are used here and the data. But once I started doing extrapolation after I get the match, you can see that there is some considerable deviation in the result, because this is a log curve. This is why this deviation is considerable. Even in this second example, you can see that the deviation is much longer. So what we actually do now, because one more time, this is all what we have now. We cannot run a test. All what we have is that we have the production, the actual production data. So what, and then this production data, I don't know which model to use. They're all match very well. So what we do now is that we actually average this, use the alternative model as the same fit. Then we're actually do a model averaging. We average the results from all the models. Some of them is we average, we're seeing the generalized likelihood estimate, which you give a weight to each model based on how good it matches the data, and then we do the averaging. And also sometimes we say, I'm not going to actually look at all the models. I'm only going to look at the top 2 or 3, and I'm going to do the averaging with them. And I do the work. Another way of doing it is that you say, okay, I'm going to only look at, I have the rate transient analysis, which is similar to the pressure transient analysis. I'm going to try to find out if I can do some diagnostic analysis, find out if I have some linear floating from the fracture, some data that show me the reservoir volume from the stimulated area, and I do the history matching with that, and do the performance predictions based on that. The same thing, so the workflow we do now, we got one of the things you remember that in order to have successful unconventional flow from gas reservoir, we must have a very large number of wells, because each well cannot produce a whole lot. So in order to have commercial success, I have to produce a lot of work. So the main reason for that picture you see on the right is to show you that we have data from lots of wells. So after we access the data, we do the quality control, and then what we do is that we group this data. Every group of data that are similar in the behavior, we call them one group and analyze this one group. We cannot analyze all these wells, so we're gonna group them and we analyze. From each group, we will select a representative well, and we will do the decline curve analysis on it, and then we will do generalization for the rest of the information. Another way of doing the analysis is to actually use numerical calculations or reservoir simulators, but you need to have simulators that actually have in it the exact physics that we have, horizontal wells with different segments of fracture, and each segment has in it several fractures. You also need to recognize that these fractures are connected to the natural fracture that exists in the reservoir. So what we do is we actually specify the basic reservoir or well pressure PVT data. We load the pressure and the rate data that we actually calculated. And if there are some basic flow regimes we can identify, we do that. For example, we can say, yeah, we identified the part of the data that are controlled by the fracture. We identified the part of the data that is controlled by the volume of the stimulated area. We identified the part of the data that are telling you that was beyond that. So we can do that, and then we can do a perform some basic analysis by the analytical modeling, and then we take this data and transfer it to a numerical model, and that numerical model, one more time, hopefully will have in it all the different modification complexities that exist from that. And then once we look at the behavior of that numerical model, we probably will have to fine tune it. In other words, we have to change the values of the reservoir properties and the fracture properties in order to do a better match with the data. And then we use this model in order to generate decline curve analysis plots and do that for be able to predict the performance. That's the main thing we're trying to do. We're trying to predict the performance of our wells so we can actually do the economic evaluation and figure out how to manage our field. I think this is the last slide I have. So I am going to stop talking and see if there are any questions that you all like for me to answer.
Thank you, Dr. Medhat Kamal, for a very informative webinar. I'm sure the audience benefited greatly from it. In the meantime, there are a few questions for a quick Q&A session. So the first question is, sir, please, could you throw some light on what is meant by boundary-dominated flow?
Okay, boundary-dominated flow means that you actually have produced your well long enough such that you are now reaching the boundary of the reservoir. So let's say that you started producing your well. At the very beginning, you're changing the pressure right around the well bore. And as time goes by, you're going to start reducing the pressure far away and farther away from the well until you get to the point where you actually reach the boundary of the reservoir. Once you reach the boundary of the reservoir, you are no longer producing under what is called transient flow or unsteady state flow. You are producing under what is called pseudo steady state flow or boundary dominated flow. You reach the boundary and now the boundary is controlling your data. So that is what boundary dominated flow means.
Dr. Medhat, there is another question. Which test would you recommend for gas wells? Is it modified isochronal test?
Yes, modified isochronal test is the most efficient way of calculating the skin value, actually at the well, as well as the pressure drop because of the turbulence in the well. So the modified isochronal test is the most efficient way of doing it. That is a correct assumption.
Another question is, how can we identify basic flow regime?
Okay, you identify the basic flow regime by actually looking at plots like the Bourdais plot. Let me see here if I can quickly go back into my that was much. Okay, for example, if you have a plot where you're plotting the pressure and the pressure derivative versus time, so you can see this is the pressure derivative. When you have a flat line like that, that means that this is the radial flow regime. We actually call it the infinite acting radial flow regime. So that's a flow regime. When you have a line that looks like this with a slope of 1, this means that you have the well bore is controlling your pressure. And when you have at very long time, you have a straight line that look like this, the same slope of that line, then that is mean that you actually the boundary is calculated. This is actually considering the first question. This is actually the part which is called boundary dominated flow. Now, if you have a fracture, then there will be other lines here with different slopes. The fracture will have a slope of a half, which means that your data will probably look like a line would be have a slope that look like this, for example, half of that slope, and so on. So this is what identifying the flow regimes mean.
Another question, could you please elaborate the different regimes on the decline curve for the case of the DFIT curve?
Okay, the decline curve analysis, as I mentioned, was originally done by this is before we actually have started having equation that describe the flow in the reservoir, like, for example, the Darcy flow equation that you are all familiar with. When actually ARPS, what they were doing is that you plot the flow rate versus time. And of course, so the time is on the x-axis, the flow rate on the vertical axis. And you're going to see that the flow rate is declining with time. You are producing at the same pressure. Now, if you actually take this curve and extrapolate it a little bit, you will find out how your well is going to do. Now, there are different ARPs have different model. Just simply fitted different curve from them, and based on each one of them, you take it and you extrapolate it for a long time, and that will tell you what is the expected ultimate recovery from your reservoir. When you try, ARP's equation was for boundary dominated flow, which means that you actually produce your well until you reach the boundary. But in unconventional reservoir, it will take much longer. It will actually, as I mentioned before, will take something like about 50,000 years to reach this. So in order to reach that may be like something like about 1 million years. So although we are using, one more time, because we don't have any better to do, we are using the decline curve analysis in there, we know that it is not correct. And this is therefore, people started making other modifications to the equation that ARPS came up with in order to find out if they can better fit the production rate performance of the unconventional reservoir.
Another question is there any standard test duration for modified isochronal test, or does it depend on reservoir properties?
It does depend on the reservoir properties. What you hopefully can do is that if you can produce your wells, for every step, just long enough in order to reach that part, just long enough to reach here, then that will be preferred. Now, when you talk about reservoirs with a very high permeabilities, like some of the reservoirs that exist in the Middle East, then you are going to reach to this part here very quickly. And in some other parts of the world, it's going to take a longer time to do that. So when you design your isochronal test, you need to say there are design methods and design functions in all softwares. I mentioned the software from Kappa, which is the most dominant software in the market right now. And so when you design, you actually design your test. You in the software, you will input your reservoir properties the best you can, and then you are going to run the model, and you find out how long is going to take me to get to just the beginning of this. That's all. I don't need to stay there here. Just at the beginning of that. Then that will be the length of each one of the segments I'm using the modified isochronal test.
If we have limited data for well test analysis, could an experimental design be used? If yes, how is this applicable?
I'm sorry, would you please repeat that question? I didn't get all of it.
Okay, if we have limited data for well test analysis, could experimental design be used? If yes, how is this applicable?
Yes, you can use experimental design to do that. You can also use most of what people are using now, even better than experimental design, is that using data analytics in order to be able to do that. Instead of actually running your test, running lots of tests for a long time, you only can run only a very small number of tests properly. And then after that, if you have proper data analytics, then you'll be able to actually, in some cases, avoid completely running tests and shutting your wells in. I am going to refer you to a paper that was published in 2013 by my colleagues from Anadarko Oil Company. If you can find that in the literature very easily, and it will show you how they were able to use data analytics with testing data that were not proper or not completely complete. In order to do that, and they reach to the point at the end where they say, I really don't need to shut the well anymore. I have enough data to predict its performance.
Another question is, what are the differences between analyzing deviated wells and vertical wells?
The main difference is that when you have a deviated well, then you actually have your well bore is actually penetrating a longer distance inside the reservoir, and therefore that will show up, if you don't take care of it that way, that will show up as a negative skin in your work. So you need to be aware of that. That's the main difference between the two.
The last question is, how can we use machine learning in the workflow to obtain the accurate analysis?
There are actually a lot of paper that were done that way. And can you all see a slide that says application of machine learning in transient surveillance? Can you see
sir.
that?
Yes, sir,
Okay,
I can see it.
let me see if I can expand it. Okay, one more time. Let me go back. Okay. All right. What you're looking at here is that you are looking by some real nice work that's done for to answer the question, machine learning and transient surveillance. This work was done by people at Chevron. What do they have here? What do they have here is that they have a reservoir, and this reservoir is it's actually I don't know if I can say the name of the reservoir or not, but it doesn't matter. This reservoir is an offshore reservoir. The wells are equipped with bottom downhole gauges, and this way they are having a lot of buildup. Every time somebody shut the well in for any workover, they have buildup. Now they have a very large number of buildup tests. And what they did, and their work, by the way, is published. You can find all the details in this SPE paper right there. So what they did is that they actually took the data from some of the wells, and they actually applied machine learning models to it, and they were able to find, we're going to do the machine learning because they have a very large number of tests. Every one of these is a test when all these things are in one well. So they'll say, we want to be able to use the machine learning to analyze all this data because we cannot analyze. And here are the results. They actually, for well number A, for example, they analyzed 46 tests, and just simply assuming only 2 hours per test, which, as you all know, if you analyze this is a very small number. And they find that this is how long is going to take. But now they analyzed 80 tests by machine learning, and look how long it took, 5 minutes. Now in well number B, same thing. They like, if it takes 30 wells, 30 tests analyzed by a takes 60 hours. This is only for the analysis, by the way. Then if the machine learning, one more time, 80 tests, 5 minutes. So there is a lot of good information about doing that work, and you can see one more time. I highly recommend that you look at this. You look at this information. Let me see if there is the second. No, I didn't mean to give. I was just okay. For the previous question, where we're asking about the inability to find the data. This is a work that was done by people at Anadarko. Here is the name of the senior author, and I don't want to go. There is no time to go through all the details, but they actually end up by saying that you can actually do the analysis without shutting the wells in. So there's a lot of work that's done there, and it's available to view that. One more time, if you guys have any questions, I'm sure you can. You have a way to submit your data to Dr. Al-Harji, and then I'll be glad to provide answers to them if you guys send them to me.
Thank you again, Dr. Medhat Kamal, for dedicating some time of your surely busy schedule to give this webinar. It was very, very informative. Thank you, attendees, for tuning in from all around the world. Please stay safe, wear a mask, and have a great day.
Would you please let me? I want to say something very quickly. Is that okay for me to say?
Of course, sir.
Sure. I know that one of the sponsors of that work is the Egyptian section of the Society of Petroleum Engineers, and I will be remiss without saying something about that section. The Egyptian section of SPE is the sponsor of 8 student chapters at 8 universities. This is a large number, and no section is sponsoring that. That Egyptian section is sponsoring the students at Cairo University, Alexandria University, Al-Azhar University, Suez University, Future University of Egypt, British University, Ferris University, Alexandria, and Tripoli University. So I just want to say that, give them credit for that excellent work they are doing. I know this has nothing to do with my lecture, but I cannot let that thing go without, and I know a lot of people listening to us is from that area of the world, so we need to give them kudos for that.
Thank you, sir, for your kind words. We are very honored for having you here. Again, have a nice day, everyone, and stay safe.
Thank you all.